Alright, so this is chapter 14, Chemical Kinetics. The kinetics of a reaction tell us how fast a reaction occurs, how fast product is made, or how fast reactant is used up. Reactions work at different speeds. Some reactions are extremely slow, some are very, very fast. And just looking at a balanced chemical equation, we can't tell the speed of the reaction. So the study of kinetics allows us to gather data about how fast product is made or how fast reactant is used up to determine the rate of an overall process or a reaction. We can also use this information to determine a mechanism, which we'll talk about later. Alright, when we look at reaction rates, there's different ways that we can measure the product being formed or the reactant being used. But overall, we have to look at a change in concentration of either the product or the reactant over a certain period of time. Alright, so rate is actually change in concentration as a function of time. Alright, so our delta A represents change in concentration of some reactant A. In the picture, A is the red circles that represent our reactant, versus the change in T, which is going to be our time. So over time, we notice that the red, A, turns into our product B, which are the blue circles. So by studying how much A changes over this time period, we can get rate information. Alright, so if we look at a balanced chemical equation, it's given up here, and then we can collect data on how fast our reactant is decreasing over time, we can try to measure the rate of the reaction. Alright, so this is a typical table that tells us information about time and about concentration, but it doesn't tell us rate yet. It just shows that our concentration of our reactant is decreasing as time increases. When we take the difference between the concentrations over the time, that tells us the rate information. So over the first 50 seconds, we can see the change in concentration, and we can take a ratio of change in concentration over change in time will tell us the rate of that 50 seconds. We can do this for each of the steps, so for every 50 seconds we can look at the rate. Now in this example we can see that the rate is changing. It doesn't stay constant. And if we look at the values of the rate, we can see that the rate is actually decreasing as the concentration decreases. Right? So one way to measure rate is the average rate. Average rate is looking at a particular time period. It can be 50 seconds, it could be 3 hours, but we're looking at the rate of change over that time period. If we plot all of our data points, as shown in the red line, we can see that we have a slight curve. Because our rate changes over time, is actually decreasing, we can see that our rate slows down. In this graph, where we have concentration versus time, rate is defined as the slope. Okay, so the slope of our red line would be the rate. We can see that down here. Change in concentration would be our change in Y over change in time, which is our change in X. Now because our graph is a curved line, our slope is changing. Our rate is changing depending upon the time. So in addition to looking at finding an average rate over a certain time period, say the first 100 seconds, we can also calculate what's called an instantaneous rate. Instantaneous rate wants to know the rate at a particular time point. For instance, at time equals 0, what is the rate? at time equals 600 seconds. What is the rate? In order to calculate the rate in these instantaneous time periods, we just need to know the slope at that point. So we can draw a tangent line, which is a line that meets our curved data line at the point of interest, and then calculate the slope of that line. And the third type of rate is the initial rate. The initial rate is really just the instantaneous rate at time equals 0. When our reaction first starts, how fast is it going? So again, we'd have our tangent line at time equals 0, and we can calculate the slope of that line to determine the rate. Now for most reactions, the rate will slow down over time, so the initial rate ends up being the fastest rate for the entire reaction. Now not only does concentration and time affect what the graph looks like for our rate, but stoichiometry does as well. So if we look at our reaction we had here, we notice that everything has a 1 to 1 to 1 to 1 ratio. All of our coefficients are 1. This means that for every 1 mole of our reactant that is decreasing, I make 1 mole of product. Because this is a 1-to-1 relationship, the two curves that I would see for reactant decreasing in the blue line and product forming in the purple line would be identical, but mirror images. The blue line shows the reactant decreasing, so we would have a downward slope. The product is increasing at the same rate because it has the same coefficient in the purple line, so we have an increasing slope. But they are mirror images, so if we drew an imaginary line halfway through, the two curves would be identical. We can also set up our ratio. Change in concentration of reactant over change in time is equal to change in concentration of product over change in time. Notice the only difference is the negative out front. Typically you see a negative in front of reactant ratios because reactants are decreasing. Products would not have the negative sign because products are increasing. But what if we don't have a 1-to-1 relationship for our balanced equation? If we look at this next example, H2 plus I2 gives us 2HI. We have a 1-to-1 relationship between the two reactants, but 1 to 2 between the reactants and products. So this means for every 1 mole of H2 gas we use up, we are creating 2 moles of HI. So if we study the rate of H2 disappearing, it would not have the same rate as HI appearing, because HI is appearing twice as fast as H2 is disappearing. So to set this up into a mathematical relationship, we could say the rate of the reaction is equal to the negative of change in H2 over change in time. Because H2 is a reactant, we have the negative out front, and that would be equal to half the change in HI over change in time. Because we have a 1 to 2 relationship, because we're making 2 moles of HI for every 1 mole of H2, in order to set them equal to one another, we'd have to take half of the HI rate to equal the H2 rate. Another way to remember this is that the fraction that we need in front of the relationship is the reciprocal of the coefficient. So I have a coefficient of 2 in front of HI, so my fraction is 1/2. If the coefficient were 3, it would be 1/3. If the coefficient were 4, it would be 1/4. When we look at the graph, we can also see this change based on the stoichiometry. So again, our blue line represents our reactant decreasing, so this is H2. And the red line here represents our HI increasing. So again, if we take our imaginary line through the middle, we no longer get a mirror image. We can see that the red line has a greater slope compared to the blue line. This is because we have a 1 to 2 relationship. Our HI rate is twice as fast as our H2 rate. And we can see this in the graph. Alright, so the general summary for how we can compare reactants and products comes from this formula. Rate is equal to negative 1 over the coefficient for each reactant. Okay, so the negative is out front for each reactant A, reactant B. The rate is also equal to 1 over the coefficient for the rate of product formation. Notice there's no negative here for C or D because they are products. But we can set the relationship equal to any two things in the reactants or products. So for the whole reaction, I can compare A and B, I can compare C and D, or I can compare either reactant to either product. So I can compare A to D if I wish. So the key idea behind how we talk about rate. When a question asks for the rate of a reaction, it only wants to know the initial rate. So remember we had 3 types. Average rate over a certain time period, instantaneous rate at a particular time, and initial rate, which is the rate at time equals 0. The word rate just refers to initial rate. If the question asks for average rate over a time or instantaneous rate at a certain time, then that's more specific. But if it just says what is the rate of the reaction, it's talking about initial rate. Why is it initial rate? When we get more into how we're going to calculate rates for reactions, we realize that as soon as a reaction starts, we no longer know the concentration of the reactants, because reactants are being turned into products. But when we first start at time equals 0, we know the concentration because we can calculate that based on what we put into the reaction vessel. As soon as the reaction starts, those concentrations change, and we don't know what they are anymore. So calculating the rate becomes much harder. Initial rate, because it's at time equals 0, we know the concentrations of our reactants. So at time equals 0, we have the most information about our reaction, so this is the rate that most people are interested in. The rate for a reaction is also equal to the rate for any chemical, reactant or product, with a coefficient of 1. Alright, so this means in our example with H2 and I2, where we were making 2 moles of HI, the rate for the whole reaction could be equal to the rate of H2 or I2 because they both had coefficients of 1. But the rate of the reaction is not equal to the rate of HI because HI had a coefficient of 2. So if we look at this example, 5A plus 2B gives us 7C plus 1D. Alright? So we can see we have different coefficients for each of our reactants and products. So the rate of all 4 of these are going to be different because they have different coefficients. So the rate of formation of C is 0.15 moles per liter per second. So if we know how fast C is being made, we can then relate it to A, B, or D, or the whole reaction. So in the first question, what is the rate of the overall reaction? So if the rate of C is 0.15, but C has a coefficient of 7, remember rate for the whole reaction has to do with a coefficient of 1. we would need to divide our rate of C by 7 to determine the rate of the whole reaction. What is the rate of disappearance of B? So again, we can compare our rate information for C to B. So we can divide by 7 to get our rate for the whole reaction, and then multiply by 2 because B has a coefficient of 2.